So first, let's see how to find ds using geometrical intuition. Okay? So let's say I ask you this problem. Calculate the area of the outer curved surface of a cylinder of radius r and height h by doing a surface integral. Okay? So basically what I'm asking is for, if this is a cylinder, height h and radius r. So I'm asking you for the area of this lateral curved surface, okay, the whole area around the cylinder. So how do I calculate this? So first thing is, what is the parametrization of this surface? So you can use cylindrical coordinates. So if you go to a table, or you just remember how cylindrical coordinates are written, so r in cylindrical coordinates, which is x, y, z, is rho cosine phi, rho sine phi, and z. Okay, and we have these three variables, rho, phi, and z. But in order to define the outer surface of a cylinder, what we can do is say, let's fix the coordinate rho equal to r, which is a constant, which is the radius of our cylinder. Okay, and this means that our r vector now is a function of phi and a function of z, right? And it's given by r cosine phi, r sine phi, and z. Okay, so this would be our parametric surface of the cylinder. And here I'm showing 1/4 of this cylinder. Okay, so in reality this would continue around the z-axis. It would be a full circle, but I'm only showing 1/4. Okay, from phi equals 0 to phi equals pi halves. Okay, so I'm showing 1/4 of the cylinder. So now, of course, our two parameters u and v are written now as phi and z, which means that the area of the surface we want to calculate is going to be the double integral on the whole surface of ds. Okay, so we are assuming that there is like a 1 in the integrand. Remember that we can always put a 1 in the integrand to calculate areas. So now the question is how to calculate ds. Yeah, so let's find ds by geometrical intuition. So we know that ds will be something which depends on the two parameters times the differentials of the two parameters. Okay, that's always how ds looks like. When you have a surface that depends on two parameters, you need to find this stretching or squeezing factor. So the way you find it by geometrical intuition is the following. You fix a value of the parameters. For example, phi equals phi 0 and z equals z0. So you fix a value, okay? And this leaves you at a point here. Okay, so this point is when you fixed a certain angle and a certain height. It can be any angle and any height, okay? Then you increase phi by an amount, so by an amount d phi, okay? So you increase phi, and you also increase z by an amount dz. So you have moved from being here. Now you increase phi by an amount d phi, so you increase the angle phi by a certain amount. Yeah, so this certain amount is what I'm showing here as d phi. So you end up here. And then you increase z by a certain amount dz, so we move upwards through the z-axis. So we end up here by increasing an amount dz. And this creates a small rectangle. Okay, and this small rectangle is ds, which is this small rectangle here. Now you could say, Paco, this is not a rectangle, it is curved. That is true, but if you assume that d phi and dz are differential amounts, they are so tiny that locally we are making the rectangle smaller and smaller and smaller until it's eventually a flat thing. Yeah? So it's no longer curved because we are zooming in so much. So that's always the idea behind differentials. So then this rectangle becomes a rectangle whose height is dz and whose width is r times d phi. Why is that? Because you remember that if you have an angle phi and a radius r, the arc length is equal to r times phi. Yeah, remember that's the equation for the arc length. So this arc, which is the same as this arc here, that's r times d phi. Okay, and therefore ds becomes equal to the multiplication of the length of the height times the width. So that is r times d phi times dz. And as you can see, it falls into the format that we already knew. So this function that we had to find, we figured out that this function is actually a constant. It's equal to r. Okay? So that's how we find ds for a cylinder. So now we are ready to integrate. We just do the integral of r d phi dz, and we just need to write the limits. So the limits of phi are from 0 to 2 pi to cover the whole cylinder, and the limits in z are from 0 to h, right? Because the cylinder goes from z equals 0 to z equals h. So therefore, doing this integral, this is very easy. We can do separation of integrals. First of all, the r can be taken outside because it's a constant, and then we have integral from 0 to 2 pi of d phi times the integral from 0 to h of dz, which is equal to 2 pi r h. And that is the surface, the outer surface of a cylinder. Okay? You can also argue that if you have the surface of a cylinder and you come with scissors and you cut here, and then you unfold it, you end up with a piece of rectangular paper, right? Whose height is h and whose length is equal to the circumference of the cylinder, which is 2 pi r. And therefore the area is 2 pi r h. Okay, so that would be an equivalent way of finding the area. So you see it agrees. And finally, there is also an alternative method, which is to imagine instead of a little tiny square, what if you imagine dividing the cylinder into ribbons like this, okay? But ribbons with a differential height, dz, okay? So you could also do this, that's fine. So then what is the size of this ribbon? What is the area of this ribbon? So the height is dz, so let's say ds is my ribbon, yeah? The height is dz, and what is the width of the rectangle that forms this ribbon? It's equal to the circumference. It's 2 pi r, right? So this is dz times 2 pi r. Okay, so then you can integrate ds, which is the integral of 2 pi r dz, but this time we only have one variable because our ribbon only has to change from z equals 0 to z equals h. Sorry, from 0 to h. And if you solve this integral, you also get 2 pi rz, rh. Okay, so this is another way of interpreting the integral on a surface by doing a single integral. So this is only one integral instead of a double integral. Okay, this is especially possible because we are integrating ds. If we were integrating some function inside of the integral, so if here in the double integral, instead of having a 1, an implicit 1 here, we had some function that depended on phi and z. So in this case, the function was 1, yeah? But if this function depended on phi and z, and in particular if it depended on phi, we would not be able to use this trick to integrate because throughout this tiny ribbon, the function would be changing. So we would not be able to just write f times ds, so our function times ds, cannot be written using the entire ribbon. If the function is changing with the angle phi, we do have to split into tiny rectangles so that the function is constant in every rectangle. Okay? But in many cases, the function that you are integrating does not change with phi, and then you can do the integral as a single integral only in z. Okay? Good. So that's the first way of finding the s, by geometrical intuition. And this is a very common way of doing it. And you can solve lots of problems by doing this trick of geometrical intuition.